I love that track. That's a pretty good intro track. So I had an idea for what I wanted to do today, but my plans have now changed because I got an email from the conference people that was like, "Hey, you didn't submit your thing for the other conversation. What is it called? Presentation." And like we did. They're both in there. But I think a human went in and looked at it. And they're like, "Wait, these are the same." And it's true, they are the same because both of the presentations are in the same set of slides. So now I have to break them up, which means I think we need to have a better idea of what's going to go in all of them. Just memes. Let's see. So how do we want to run this show? Basically, I guess I can just show you the slides and then just work on them. We're calling it a co-working. Let's see about this. Button. Now I'm down here. Cool. So yeah, the idea was that we would put these two things in there as separate slides so that we didn't have to, we could put off as long as possible having two separate things. So I guess let's see, I don't know how long this is going to take me actually, but yeah, I think I'll duplicate them, get a little get the content sorted out a little bit better, and then I think we can do, I got a bunch of parts to do more of the embedded system project, the compost monitor, but I haven't figured out how I want to put them together. But maybe I'll just wing it, because that's going to be more fun than like figuring out a slideshow. But here we are. So let's finish this, get it out the way, and do that. So first thing I'm going to do, I have to go over here. Can't see this, but I'm going to... can I make a copy? Here we go. Why doesn't it come up in the right click menu? Oh, it does. I'm just dumb. Okay, it's creating copy of slides. This one's just called slides. So we're going to call this, I'm going to call this lesson plans and activities for a computer architecture unit. Okay. And then I'm going to open copy of slides, because the second presentation is here. So we're calling this "Who Says You Can't Teach Low-Level Systems Topics in Java." Okay. So this one is good. All this other stuff is just like the template slides. I don't know if they can be deleted. Possibly. I don't know. Not sure. Okay, but so they begin with a thing and end with a thank you. So this is, I can just go in here, get rid of all this. Bang. Okay. There we go. And then who says you can't teach low-level topics? So this, I think we can go all the way up to here and delete these. And I think we want to delete this. Whack. Move this up. It's me and Saul. I'm not sure how it fits in here. It does. Okay, so this is trash. Okay, this we got to figure out exactly what's going to go on, but that's okay. And I think this is done. Okay. So I think that's everything. Yeah, the idea is we go through virtual memory together. Well, there's... Maybe this goes up here. So this is the intro. And then we talk about the tooling, which is the part that's like duplicated between these. Which we haven't really done because we haven't fully decided how deep we're gonna go into like, oh, it's Firebase, or like you should set this up. Yeah. In any case, oh, these should be this font here, non-bold, but then also, I guess just not bold to match these. That's fine. All right, so I think that's it. I think for the most part, these are the slides. We still need to make the landing page. Here we go. So this is lessons intro. We're gonna do new slide here. I don't know why they have this white on black. That's gonna be very hard to see on like a projector. So at least I think that's hard to see. It might be harder to see black on white on a projector. I don't know. It's been a long time since I've looked at a presentation live. But yeah, we can hit it with... These are the same. So, okay. So this is to do Firebase VS Code. We might be able to do a small demo of something. So I think that's it. We'll have to figure this out with this format. Here we go. Like these slides, these can all be copied here, I think. Paste. Why does it... I hate it. It's the same styles. Okay, so delete this. And in fact, maybe what I should have done was not delete anything from here and just have the duplicate one so that they're satisfied, and then we can go back and and fix it. But here. Who says you can't teach low-level systems topics in Java? Slides URL. Yeah, I know there's an error on the page. I haven't freaking... Okay, and then let me make sure I... Okay, done. Resource, submit. Okay. All right, I think I've fulfilled the requirement for that. Not sure what else we want to do at this point. I gotta get back together with Salt and maybe we'll do like a mock run through of them and see. But I don't know. I'm pretty happy with that. I don't super care. So let's, I guess let me, it's 3 o'clock already. I started late. And yeah. And I haven't even like opened the project in a while. So let me see. CD code. What do we call this? Compost mod? Ooh. A lot of changes here. Okay. So we were working on trying to optimize the power before doing any of the other stuff. So maybe we get back into that right now. Yeah, I mean, I did buy a bunch of like current sense resistors. So maybe that's a good place to start. Let me open up GIMP here. So I'm going to draw. It's opening. Okay. So here we go. All right. What are we trying to do? So let me edit the stream info actually. We're gonna do embedded compost mon current sensing. Later Geoguessr. If we have some time. So I'm gonna take off these tags. Embedded development. We'll go C++. We'll hit it with what are the tags? I don't know. Send me some tags, suggestions. Embedded development, software development. I mean, I don't know what else. Okay. So there's one thing I need to learn. And that is there's this idea of let me see if I can search for this. High side. There's this two ways of doing power measurements, basically. So one way to do it with like a current sense resistor. So the idea is, you know, you have some kind of power supply, right? And then you've got your system, we'll call this sys, right? And it's fed from this supply and out to some, you know, ground. We'll call this a load. So if you're going to measure the current, you want to place like a measurement device somewhere. One way to do it is to paintbrush. What am I dumb? There it is. Whoop. 51. No, smaller. That's fine. One way to do it is to put it up here, right? And then suffer the voltage drop that happens across this resistor. We'll call this RH. And then so you can measure, you know this is at some voltage, nominally V voltage supply. And then there's some voltage drop across across RH, VR, H. And that means that you'll have a voltage drop here, so then this is VSS minus VRH is now the voltage that is supplied here. So VSS minus VRH. That's the... Whoa. That's sort of the trade-off now here. So this voltage now needs to account for the fact that there was a voltage drop here, which is usually fine, especially if the current sense resistors are really small. It's over there. They're like tiny values, like 0.01 ohms or, point something like that. Tenths to hundredths of ohms. And so if the whole current of the load is going through it, you can measure the voltage across it and then get a sense of what the actual current consumption is of the thing, which is cool. So that's fine, but this is high side. The high side current sensing, right? Because it's on the high side. The other thing you can do is very similar. You got your VSS. You got your load. But then what you can do is put, all the current has to go to ground. So you can put it here. And this is a low current, same type of sensor, same type of current sensing, but there's a load here. But now, I guess I'm not sure. I need to know what the trade-offs are of doing this. Because this is a choice you have to make. Why choose one over the other? All the formula is the same. There's a voltage drop from here to here. This needs, say this needs 3.3 volts. Well, then there's some non-zero voltage here. This has to start at 3. Well, I'm just making up a number. Let's say it has to be at 3.5, so that over here, the voltage... Well, how would you do that math? That's a good question. In either case, this does not go... It's not going to go below 0. But it does need to go lower than the low point here. So what's the trade-off? And that's what I was doing here. So high side versus low side current sensing. I looked this up at some point, I guess. What's the difference between high side and low side resistive current sensing? When each is more appropriate? Okay. Look at the two arrangements. Resistive current sensing is widely used on printed circuit board assemblies when dealing with low to moderate current levels. Resistors placed in series with the load and the voltage developed across the resistor is measured to determine the load current. Yeah. Current sense resistors usually have values milliohms range. Note that even with small resistor values, the shunt power dissipation can be an issue, especially for high current applications. 100 amps, even at 1 milliohm, is still 10 watts. A small resistor value also leads to a small voltage drop across the resistor. That's why an amplifier is needed to convert the small voltage developed across the shunt resistor to a sufficiently large voltage suitable for upstream circuits. We'll discuss that in high-side current sensing. The amplifier can have stringent requirements in terms of the common mode rejection ratio spec. Okay, yeah, this is what I was showing in my crappy diagram. There's a low-side sense versus a high-side sense. What are the advantages and disadvantages? Okay. Assume that our shunt is 1 milliohm and current is 100 amps. Even at this large current, the voltage drop is only 100 millivolts. Therefore, the common mode value of the voltage across a low side shunt resistor is only slightly above ground potential. And for the high side configuration, the common mode level of the voltage across the shunt resistor is very close to the load supply voltage. Since the amplifier used in low side current sensing deals with a small common mode voltage, it doesn't need to have a high common mode rejection ratio. Common mode rejection ratio specifies how much attenuation an amplifier exhibits for a signal. Since the common mode value is almost 0 for a low side current sense, the amplifier requirement is significantly relaxed. Consequently, you can use a simple amplifier configuration. Okay. Wow. In this example, this one, figure 3, amplifier consists of an op-amp and 2 gain-setting resistors. Note that this is actually the non-inverting configuration of an op-amp. This is the more familiar schematic of the amplifier shown here. Is it any different? This is the same. Okay. V out is 1 plus. I do have op amps. Many high side current sensing applications. Okay, the low side method can cause ground loop issues. Although the low side sensing method simplifies the amplifier design, it has a few disadvantages. Low side current measurement places an additional resistor in the ground path, hence the ground of the monitored circuit is at a potential slightly higher than the system ground. This can become a problem for some analog circuits. Since the ground of the monitored circuit is not at the same potential as the other loads in the system, there might be ground loop issues leading to an audible noise or even interference with nearby equipment. Yeah, cost-sensitive motor control in applications such as drones, drills, and reciprocating saws typically employ low-side current sensing. Okay, that's interesting. Low-side method cannot detect fault detection. It feels like there's too many detectings going on. There are various fault conditions that low-side current sensing cannot detect. Okay, figure 5 shows an example where a short occurs between the power supply of the monitored circuit and the system ground. Okay. The fault current, I short, flows from the bus voltage directly to the system ground and does not go through the shunt resistor. Hence, the current monitor circuitry will not detect this fault condition. Low side current sensing also cannot detect a short between the ground of a monitored circuit and the system ground. Right. Yeah. 2 wires are needed to power the monitor circuit, even if the system ground is available. For example, in automotive applications, the car chassis serves as a common ground. With the chassis being at the system ground level, we only need a single wire for powering a load. However, if the current through the load is monitored by the low side measurement technique, the system ground cannot be used and 2 wires are required for the load. Yeah, I guess that makes sense. Low side current sensing usually used in cost-sensitive motor control. Okay. Let's see. What does TI have to say about this? Texas Instruments. This is a presentation. Direct versus indirect, high versus low. Op amp, diff amp, inst amp, or CSM? I know what... Well, I've heard of 2 of these things. Operational amplifier, op amp. This is short for instrumentation amplifier. What is CSM? I don't know. Indirect sensing based on Ampere and Faraday laws. Generally, this method is like not good for low power systems. You gotta get too accurate, too precise. So that's not it. Indirect sensing with Hall effect sensors. Yep. Direct sensing. This is exactly what we're talking about. Recommended for smaller currents, power loss, low voltage, load current not very dynamic. Yeah. Diff amp. Differential input amplifiers are devices that can input and amplify different signals while suppressing common mode signals. This includes op amps, instrumentation amplifiers, difference amplifiers, and current shunts monitors. Is that CSM? Cool. Cool. Why not just use the op amp then? Common mode voltage. What is this saying? What is VCM? Is that the voltage measured here? I'm confused. Low side. Pros. Cons. Yeah. Pros. Can detect loads. VCM is approximately V-bus. What does that mean? Common mode voltage. I mean, that's the... I'm unsure what the diagram is saying here, but like basically... The way that I learned about common mode voltage was that basically because these are right next to each other, any noise going in one end will also be going into the other end. And that's where the common mode rejection ratio stuff comes into play, where like, you know, common mode voltage. Common mode signal is the identical component of voltage present at both input terminals of an electrical device. Common mode interference, right? Voltages, these conductors are, and the common mode signal is the average of the voltages. When referenced to the local common or ground, a common mode signal appears on both lines of a two-wire cable, in phase and with equal amplitudes. Yeah. May require current sensing in both directions? Oh, we're not doing that. But I suppose this would work, right? I do have an op amp. Somewhere. I'm pretty sure I bought a set of op amps at some point. So I have them. So I was going to do some guitar pedal experiments, but never ended up doing them. So, alright, what does this say? Op amp, low side only. Difference amplifier. Can be used for either. I thought I also bought. Let me grab what I have, actually. Give me one sec. Okay. Here are some of the current sense resistors that I bought. Let me make me bigger here so you can actually see them. These are rated at 0.1 ohms at a tolerance of 1%. I also have this INA 219 module. Now I think this can just measure stuff for me, but I have to look up how to put it. So let me grab the data sheet for that in a sec. I also got an alternative for the SHT sensor that is in the probe. It's over there. These are the SHT 20s, which are more affordable and theoretically kind of breadboardable. So if someone's following along with the videos, they should be able to get this plugged in more easily without having to buy as much stuff. The heck is this? Oh, right. I also got stuff to try to measure the current, but I don't think this kind of thing is going to work well because it's the problem with these is they cannot tolerate, there's like a limit to them. So once you go up past the 50 microamps that this has the max displacement of 50, once you go past that, it doesn't allow more current through. So that's a problem because the idea is like the current's going to spike while it starts up, or while it's doing stuff, current spikes, but then we have no way of measuring the small current after the spike, which is what we're interested in. I don't care about the spike, I care about the small, most of the time, current. Also about this, you know, this box thing, which lets you select resistors. So this is good for like demos, is what I'm going to use it for. To demo, you know, as you change the resistance on a particular circuit or whatever, then what happens as a result. There's these RGB LEDs. I bought a bunch of these because I'm not sure why, but mostly because I don't want to have people purchase like hundreds of LEDs, and we can demo different stuff with these. Just use one of the pins or whatever. I don't know. Maybe it was an impulse buy. I don't have any RGB LEDs, so now I do. And then, what the hell is this? All right, more oscilloscope probes, because I actually only have the one, which is not very useful if you're trying to measure two things. So that's that. Okay. This is the op amps that I have. TL082. I don't know what they are. TL082. Let's look these up. Well, yeah, let me look those up to make sure. TL082. Dual JFET input operational amplifier. Okay. What are they good for? Plus minus 15 volts. Plus or minus 30 volt input range. Sure. Okay. Low cost, high speed, low supply current, large gain. Such as high-speed integrators, fast DA converters, sample and hold circuits, and many other circuits requiring low input offset voltage. Okay. Yeah, so this sounds like the kind of thing that's good for like audio, maybe. Yeah, in fact, they have a tone control circuit here. Instrumentation amplifier. When you get 4 of these together. Butterworth filter. Those are fun. Ohms to volts converter. Interesting. Okay. So, might not use that if the other chips here are able to do everything together. So, this other thing. Let's see. This is the INA 219. INA 219. I don't want to open it, but I also want to look at it, so I guess I'll open it. There it is. Does this look terrible? Because in some of the pictures, the solder job looked real bad. This looks fine. Yeah, this looks fine. So that should work. Yeah, some of the images on the Amazon page for this were concerning. Yeah, so let's get some docs for this. Okay, the INA 219 is a current, shunt, and power monitor with an I2C or SM bus compatible interface. Yeah. Monitors both shunt voltage drop and bus supply voltage with programmable conversion times and filtering. Enables direct readouts of current in amperes. An additional multiplying register calculates power in watts. 16 programmable addresses. Available in 2 grades, A and B. Well, what grade is this? Would it be the... Wait. How do we know what... I don't know what shit is. Is this grade A or grade B? B has higher accuracy. Higher accuracy. I cannot tell. A8EGH, something like that. Yeah, where how do we determine the A versus B-ness and whether it matters? INA 219A or 219B? Aha. So this one just says this says I219A. So this is an A circuit, I assume. That's fine. Cool. What is the difference here? Ah. Offset voltage. Smaller there for the Bs. And I think that's most of it. Also, error over temperature. A little bit better. No extra speed. Okay. Yeah, so I think we can... Let's see. Provides C functional, basic ADC functions. Okay. Where our device goes? Oh, this is the device. I see. Okay, so then the shunt, yeah. And so this little breakout, the shunt is external. Oh no, do we have to replace the shunt? Typically less than 50 millivolts. Yeah, because this says R100. I am not sure what that means. I'm not sure what that means as a practical matter. R100. R100. How does it... Oh? Is that where the decimal goes? I see. So if it were 1R00, that'd be 1.00. Right? We would do that. Okay. That's cool. Oh, hello, Zogd. What's going on here? I'm looking at some data sheets for a current sensing thing, because my compost monitor device needs to live on a 9-volt battery for as long as humanly possible. And so I have to figure out how much current is actually consuming, and then debug why it's taking so much when it should be doing nothing at all. Yeah. And yeah, eventually I'm going to be making some YouTube videos that go through the whole process of developing this thing. But first I need to get it developed before I can teach someone how to do it. I got to be able to do it myself. But yes. I'm glad you think so. There are folks much smarter than me at this. There are too many volts. No, not quite volts. So the way current works, well, I don't know how familiar you are with the concepts of electricity and like power and all that kind of stuff, but basically the volts stay the same, but if the system is turned on, all the little bits of it draw current at some volt level, which changes the amount of power. Electrical power is see this? Power is V equals no. Power is current, which is I, times V, the voltage. So the voltage is always kept the same. A 9-volt battery stays at 9 volts no matter how much stuff you put on it. And what ends up happening is that I goes up, V stays the same, that means power goes up as well. The other important equation in electronics is what we call Ohm's law. That's V equals I times R. So in a circuit, you've got something like a battery. You've got, so this is 9 volts here. You've got some resistor R. And then that means there's some current I that goes through the resistor and out to ground, back into the battery on the other side. This whole thing is described with V equals IR. So this is like the simplest circuit. You could think of the resistor maybe like a light bulb or something like that. That's going to pull electricity and do something with it. And this describes the relationship. Now, when you get to more advanced circuits like computers or chips that actually do some fancy stuff with transistors and all that kind of stuff, then this R is no longer just a resistor. It's actually like we call it an active component. And there's a whole bunch of other types of things that go into a circuit, like capacitors, things called inductors. There are transistors, amplifiers, all that kind of stuff. So they do other things that change how this works, but ultimately this still kind of always holds, even though the resistor is not really R. We say that it's some Z for impedance. I don't know where the Z came from, but there you have it. But yeah, V equals IZ, and the relationship basically still holds, even though the circuit does fancy stuff over time. If you're just taking a snapshot, you get a pretty good idea. So what I'm trying to figure out, I was looking at before, was we can measure how much is being pulled through by our system if we just stick a resistor either at the high side or the low side and then measure the voltage across it and use V equals IR to figure out how much the I is. So we'll know R, we know V, and then we just calculate R from that, or I from that rather. But I had also purchased this little device that supposedly does exactly this for you. The measurement aspect of it completely. So you just read it out. And I was just looking at the data sheet for how to put it all together. Yeah. Here it is. That's this guy. Oh, tiny. So that's the chip that collects all the information is right in the middle there. And then that R100, that is the what's called the shunt resistor from this data sheet. So this R shunt value, we basically plug in, somehow we're going to have to put this into our circuit. Now I haven't set up my other camera, and the space is not looking good. Got a lot of crap. But let me see if I can just plug it in. Let me turn this guy on. Yes. I'll be safe, yeah. It's the voltages I'm working with here are pretty low, so generally they're not going to be particularly dangerous, even if I do end up getting shocked. Usually we're talking like 5 volts, maximum of like 20 milliamps, which is going to be relatively benign. Here we go. Set this guy to webcam mode. And I should have this somewhere. This workbench display. Overhead camera. Whoops. There it is. You cannot see this because it would probably make you sick. Hang on. Hang on. Hey, there we are. I had this set up better at some point. But that's a breadboard. And that's where the whole thing is. Why is this here? But that is the actual microcontroller that gets the programming. And it knows how to run all the code to measure from this thing, which is a temperature and moisture sensor. And then this is also a different kind of moisture sensor. And the idea is that device sits, I'll package it up, package all that stuff up, throw it into my compost bin, and then eventually it should sit there on a battery and just upload data to a little server I've got running on my home network. So that's the idea. What do you think? Not seen this since school days. Yeah. If you were in like an electrical engineering kind of adjacent field, computer engineering, electrical engineering, this is the kind of stuff you did. Actually, this circuit down here in the corner of the breadboard, actually, that is from my time in college as well. I never took it apart because it was kind of useful to have. At some point, I replaced the LEDs with that bar, but it was basically like a debug circuit that you could turn on different individual LEDs with the green wires here, these connections. Pretty cool. Yeah. Anyone can be a STEM person. You just have to be interested in it. Let's see. Okay, so I think what I need to do is solder this together. So that'll be fun. Not really set up right now to do that. Thanks, man. Catch you later. Always love explaining what the heck it is I'm doing here. People are always surprised when they come on, and like, no, it's not too tough. And you just have to know a few things. I think if I can do it, anybody can do it. What does this have? It's got little posts. And then some header pins. Maybe I will solder it. Stuff out of the way. Don't need those LEDs. Just cleaning this stuff up. And then why does it refuse to keep a zoom level? So oh, I think I was pushing the volume with my tripod.
T'es prêt?
There we go. Cool. Back, in case anyone's curious, this is what it looks like in the box. Now, I need to do some soldering, which is always fun to record because the mic is on the wrong side. Bonjour. It's fine. Extension cord there. Plug in. I don't actually know how to do this. There we go. Gonna move that off to the side a bit. While I grab a different breadboard I can solder on. Blue, blue, blue. Hello. Welcome to soldering. Oops. Hi. I'm over here now. Which isn't going to work much better, actually, because it's going to be tough for you to actually see what's going on. First thing I need to do is get some water. There we go. Thought I had another spool of solder. I do, but this stuff is kind of thick. So I guess I'll open the other one. Yeah, since I can't find the one I thought was open. I guess we have to open this one. How the heck? Is it there? Yeah. Come on. Come on. Yeah. Do I need like a knife? What is this? I do have a small little... like a multi-tool. But I've almost got this. Found the tape. And the other thing I need to do is change the tip on this thing. That's the only ones I have. No, that can't be. Got them. But these are for like a different soldering iron that I don't use very often. But actually it might be fine. Well, let's see. We'll see how it goes. We'll learn by doing. Oh gosh, there's more tape on this. There we go. .7% copper, 99.3% tin. Lead-free solder wire. Oh, actually, does this not have flux? Where did I get this? And why is it so underspecified then? I might just use the other ones if it has flux. Because I don't have separate flux myself. Okay. The heck? It's like this thing's... Oh, it's missing a feedy. I hate it when this happens. It gets totally misaligned. Oh boy. Alright, we gotta shove those back in. Get them even, maybe? Oh, crud. I'm just gonna use one of these other ones. Let's see. What do we need? 1, 2, 3, 4. These are the right pitch. One, two, three. 1, 2, 3, 4, 5, 6. V in minus. Supply, ground. S clock and S data. So 1, 2, 3, 4, 5, 6. Are the holes in this thing just too small? Like, I'm having a really hard time getting them in. Unlike on the other breadboard. I guess I'll just use that one and try to... make sure the other thing is out the way. Okay. Let me see if I can zoom in. There we go. That's where we're trying to get in. I need light. Okay, that's not working. Tip is way too thin. So I need to grab a different tip. I don't know if you could see me struggle with that. But also now we gotta wait for this thing to cool down a lot. Anyway, how's your Tuesday? Mine's all right. I should change the stream description here. We're adding a current sense circuit to compost mon. And later, Geoguessr. Oh wait, no, that's already up there. Compost current sensing, later Geoguessr. Okay, it doesn't have the updated stream info on OBS. Still hot. Just trying to cool it off. This is riveting, by the way. I know. There we go. Hot swap successful. Okay. Done. Sweet. Okay. Now, so we have, sure. So we have that. We have that circuit. It has all these things already. We have to figure out where to plug it in. So let me clean this up a bit. Standard view. We got rid of the screen anyway. There we go. Okay, so we got there. So we've got a that regulator hooked up here. And we want to inject our device back in somewhere. So we need a 3 to 5 volt supply voltage. So we can't just use battery voltage. We have to use the regulated stuff. All right, you can't really see that. Maybe that's a little easier to see what's going on. No, it's impossible to see what's going on. But basically, that needs to go onto the I2C bus. Which means we need some cables, some wires. So here's the red one, supply. VCC. That's fine. We got VCC. Oh, you can't see this. You got VCC. We need a ground. S clock. I got a sticky note for this. S clock. Yellow is S clock. Gotta grab a yellow one here. SDA, we're using green or blue. And I think that's it. There we go. Hard to see. If we do it a little bit at an angle. I have to figure out how to organize this a little better. So now the question is, how do we attach to VIN? Because it's configured for shunt and bus voltage measurement. Conversion ready bit. Current and bus are converted at different points in time. Wait. Okay, wait. Back to the top. 2 grades. Okay. What's the... I assume... Let's see if we find typical application. Where was that? Here. Yeah. Power supply bypass. Input filter circuit consisting of those is not necessary in most applications. Leave unpopulated unless filter is needed. I assume we have pull-ups. I think already. I think we've already done that. Use the internal pull-ups for SDA and SCL. Supply voltage. Already have that. And then V in here and here. Power to power bus. Power bus. That's weird. Okay. Why is our bitrate so wild? Oh, is it because I have Wi-Fi on again and it's trying to use Wi-Fi? I don't know. Shows a nominal 10 amp load. So readings for the calibration example. Do we need to calibrate it ourselves? That's weird. It can be 5 volts. Load power supply voltage monitor can be size 26. Place the required power supply bypass capacitors. Layout guidelines. Okay. I think that's in there. Okay. So then what is... Where's the how you talk to it? Portion of it. Was it that table? You just read these values? Okay. Calibration register is calculated based on blah, blah, blah. Current LSB uses this value to convert the value in the current register to the actual current in amperes. Highest resolution for current register can be obtained by using the smallest allowable current LSB based on the maximum expected current, as shown in equation 2. Maximum expected current is like 20 milliamps. Divided by 2 to the 15. 20 milliamps divided by 2 to the 15. $20 milliamps divided by 2 to the 15. That's 6 times 10 to the minus 7. Ugh. That's... So 10 minus 6 is microamps. So would that be... 61 micro... No. 0.6 microamps. That's what that means. That's pretty good. I think that's all we want. That's all we need. Program value for the LSB of the current register. $10 microvolts. What? Okay. Bus voltage register constants will be shifted right by 3 bits. I'm confused about what registers it's talking about. Let me see. I squart's the interface. Address here. Open drain lines. Reading or writing. Yup. Yep. Typical stuff. Mostly I'm interested in this. Okay. A bank of registers for holding configuration settings. There's a block diagram somewhere. Yada yada. Register contents are updated 4 microseconds after completion of the write command. Therefore, a 4 microsecond delay is required between completion of a write and a give to a blah blah blah. Completion of a write to a given register and a subsequent read of that register without changing the pointer when using STL frequencies in excess of 1 megahertz. I don't think we're going to be going that fast. I think some of our other devices have much lower speed limits. There's a configuration register. Wait. We do actually want to know. Timing. Right word. Okay. Accessing a particular register. Write the appropriate value to the register pointer. Writing to a register begins with the first byte transmitted by the master. This byte is the slave address with the read-write bit low. Updates the register pointer. Wait. The next byte is the address of the register to which data will be written. The next 2 bytes are written to the register addressed by the register pointer. Generate start stop. When reading, the last value stored in the register pointer determines which register is read. So you first write register pointer and then no data. Then generate a start condition and send it to the slave. Okay. We can do that. So every read, we have to first write to it. Does it auto increment? Master determines blah blah blah. Not acknowledge or generating start stop. Write word, read word. We're going big end as well. I'm going to turn off Wi-Fi and hopefully not kill everything. Network. How's that? Bitrate unstable. Why though? Oh yeah, it's pretty low. This is low bitrate. What if I do this? Yeah, that's kind of bad. Wow. Yeah, let me know how bad the bitrate is. It doesn't look too terrible in the view I have. It's just kind of stable, but still functional. Yeah, I don't think it has an auto update. Oh yeah, it drops to 2.6 kbps. Or 2.6 mbps, because it's 1,000. Okay, registers. Configuration register. Bus voltage range, PGA gain, ADC resolution. Where does it explain how the data in it is formatted? What it's for? Right here. Should have just kept scrolling. 16-bit register. They're actually 2 8-bit bytes. Yeah. That is equivalent. Reset bit. Generate system reset. Self clears. Okay. Bus voltage range. 16 volts full scale range. I don't think that's necessary. I think we can drop that. Does it hurt or help? BRNG. Yep. How does that change anything? Because does it like improve any of the performance based on? This parameter only expresses the full scale range of the ADC scaling. In no event should more than 26 volts be applied to this device. Yeah, so what is it doing? Yeah, I'm confused by what that does. Does it do anything else based on that value? That is unclear. Okay, we're back to normal bitrate. I don't know why the computer likes to do that. Okay. Yeah, I don't see it doing anything else. BRNG1. Based on statistical analysis. Yeah, okay, I'm not sure what that does. I don't know if we need to change this value at all. Bus voltage range. Full scale range. Does that mean we can get more precise? I don't know. PG. Shunt voltage only. Sets PGA gain and range. PGA defaults to divide by 8. 320 millivolt range. Okay. ADC resolution. Shunt ADC resolution. Mode/samples. I suspect we might need to be precise. Seven, 8, 9, 10. Why isn't it in 2 tables? It should be in 2 tables. They make it confusing. Shunt voltage register. Ooh. Calibration register. All right. So this is what we got to do. An important aspect of INA 219 is that it measures current or power if it is programmed based on the system. The device measures both the differential voltage applied between in plus and in minus, and the voltage at in minus. In order for the device to report both current and power values, the user must program the resolution of the current register and the value of the shunt resistor present in the application to develop the differential voltage applied between the input pins. Both the current LSB and shunt resistor value are used in the calculation of the calibration register value that the device uses to calculate the corresponding current and power values based on measured shunt and bus voltages. Okay. After programming the calibration register, the current register and power register update accordingly based on the corresponding shunt voltage and bus voltage measurements. Until the calibration register is programmed, the current register and power register remain at 0. Okay. Calibration register is calculated based on equation 1. This equation includes the term current LSB, which is the programmed value for the LSB for the current register. The user uses this value to convert the value in the current register to the actual current in amperes. The highest resolution for the current register can be obtained by using the smallest allowable current LSB based on the maximum expected current. Used equation 2. While this value yields the highest resolution, it is common to select a value for the current LSB to the nearest round number above this value to simplify the conversion of the current register and power register to amperes and watts respectively. The shunt term is the value of the external shunt used to develop the differential voltage across the input pins. The power register is internally set to be 20 times the programmed current LSB. Okay. Okay, the shunt voltage is calculated by multiplying the shunt voltage register contents with the shunt voltage LSB of 10 microvolts. Okay. Okay. Value of the actual count, da-da-da. Yabba-dabba-dabba-da. For example, set the calibration register such that the largest possible number is generated in the current register or power register at the expected full-scale point. This approach yields the highest resolution using the previously calculated minimum current LSB in the equation for the calibration register. Wait a minute. I guess if I don't know maximum expected current. Maximum expected current. Max current ESP32. Uh, 260 milliamps. Coil power. These folks are asking about that. $40 milliamps. Okay, let's say. Well, I'm gonna write down somewhere. Got my little note here for a bunch of random little notes, but there's just a reminder. We're assuming we'll say a max of 500 milliamps, and then maybe we'll refine and or calibrate from there, because I don't remember what we've seen in the past. I don't think it goes above like 20. Realistically. Okay. So maybe let's try programming some of this, actually. Bye-bye GIMP. And we'll open up the compost probe. And head in for main. Come on. Tiny windows. We'll make this bigger here. Okay. So we need to monitor on our I2C bus. Let's see. Bus. Right now, the only thing is that probe. Because did we turn off the screen? Did I just delete it? Display, screen, what was it called? It's in here somewhere. Sharp display. Yeah, that's gone. Okay. So I'm going to create a class then. In here for the moment, but we'll move it. Class. What do we call this? Current sense. Or, what is it called? What does it call itself? Current/power monitor. Okay, we'll do power monitor. Which has, and if I follow the form, maybe of the sharp display, because I just had that open. This requires the I2C bus, and it's going to have an address. And it will hold on to a device on the bus. So, yeah. So I've talked to some folks in the past. They talk about dependency injection in C++. They were always like, it's bad. And if you need a framework to do it, yes, that's bad, because you've completely gone kind of off the rails. You've jumped the shark into needing a framework to do something kind of basic, which is, if you depend on something, take it as a parameter, as opposed to, like, in the constructor reaching out to find whatever the I2C bus is, and then hooking yourself up to it in a way that is less extensible, right? Rather than doing that, just take it as a parameter and then hook yourself up to the thing you are given. That's pretty straightforward. It doesn't get in the way. It's quite straightforward. It's easy to explain. And then it makes the dependencies in the code obvious. Okay, so let me... I've called it power monitor. So my power monitor, PowerMon, that's how I've been doing it. It needs a bus. So there's the bus. And then its address is a wildcard. So I have to look at it closely. A0 and A1 look unpopulated. Which I assume means they're grounded, maybe? So I guess we can work with that as an assumption. Wait, what is this? Yeah. These are pin logic levels for each of the 16 possible addresses. Uh-huh. So are they not ground, or are they ground? And how many bits is this? 1, 2, 3, 4, 5, 6, 7 bits. Okay, so that's 8. Eight zero, I think. Let me look at it more closely here. I've dropped it. Got it. Yeah, so A0 and A1 are not populated. I don't know if that means they're on the left side here. Oh. You can see it's not populated. I think that means 0, 0. But it's hard to tell. These traces are not obvious. Are they pulled up? Are they pulled down? I don't know. Let's assume address 80. Because we've... Here it's 44 for this SHT probe. And, well, let me see. Let me check on... Let me check on this. I didn't document for myself how the address works. So adder... I2C bus, I2C device, I2C device has an address. Shoot. I can never keep this straight. This is my least favorite part of how I2C stuff works. If I give it an I2C address of that is 7 bits, does that mean it should or should not include the 7th bit? Or the 8th bit, rather. So 44 is 100 010. SHT XX datasheet? Whoop. This one? Max voltage on address, address pin, address. Table 8 for respective addresses. Where's table 8 here? So it's either 44 or 45. And the way it has it here, okay, it's just the 7 bits. So then we should not shift this up. So this is not 8. This is 4. Where'd it go? Here. 400. Okay. And then does it have any methods that we need? So we need to calibrate. Well, let's see. Let's start with configuration. Voltage range, PGA gain, resolution averaging. I think that stuff default is probably going to be fine. Just to see it kind of working maybe, and then we can deal with the details of that later. But how do we write to the pointer again? Is that not something we can directly access? No. Okay, so that's just part of how we read it. So find the instructions for calibration. Programming the calibration register. Here we go. Write calibration. And how does that look? Okay. So we'll have a value. Let's see. Let's move this over here. Move that over there. Close the sidebar. We have to do this calculation. Okay, so const expr current LSB do we need to say what type in the new? I don't remember. It's been a while. C++, new function syntax. No. C++ function declaration auto. Function declarations. Inferred. That's kind of what we want. Okay, the current LSB is max expected current equals, we'll say, oh boy, 500 milliamps. Say, yeah, milliamps. Return max expected current in milliamps. Well, no, we wanted in amperes, right? So that'd be 0.5. No. 5 milliamps? No, for saying 500 milliamps. Yeah, 0.5. So then return 0.5 divided by 2 to the 15, which is that 65? 535? No, that's half of that. 32. Oh, it's 7. No. Yes, 7 FF F, because that's 16 bits. We want 15 bits. So shift it over by 1. You would have a 0 there in the highest bit, but then there. So this is 0.5 divided by 2 to the 15. 2 to the 15. 2 to the 15th power. 32768. Okay. 2 hex. So just 8. 1, 2, 3. Okay. Const Expert Auto Power LSB. Return current LSB times 20. And then Const Expert Auto calibration value is 0.04. Is 0.04096 divided by the quantity of current LSB times const auto R shunt, which is 0.100. Whoops. Ohms. R shunt. Oh, const expert. There we go. Amps. Current LSB max. Okay, I don't know why I did that. So max expected current divided by 2 to the 15th. That's max expected current. Calibration value. There. So to write calibration, let's see, into the programmed value for the LSB for the current register. Okay, use this value to convert the value in the current register to the actual current in amperes. Highest resolution for the current register can be obtained by using the smallest allowable current LSD based on maximum expected current. Sure. Well, what would we have here? So if I print this out, C++ compile time print. I guess you got to use a static assert. Yeah. Wait, how do they do this? Static print. Okay. How? Oh, I see. Okay. That's tricksy. Weird. Most recent compilers as of 2020. Huh. I'll just do a static assert. Static assert. False. And calibration value. How does this work? Static asserts. Bool const expr. Constant expression. Static assertion. Static assertion with user generated error message. Oh, so we want to do false. Calibration value? No? I don't think it knows how to do the... I don't think it knows how to do that. I just want to evaluate how this is actually printing stuff out. So C++ compile time print. Let's go back to that. That class... The class approach was decent. This. We'll be able to delete this. And then this comment says, get rid of that by inheriting from false type. Type traits. stood false type. False type. Is it dead? What happened to it? Checker calibration value. Non-type template argument of type double is not yet supported. And it says sorry. Alright. Stood integral constant bool false. What? Static thingy. Maybe checker is a name that exists. Static thingy. Yeah, non-type template type. What? So let's load. Shoot, what is it called? Is it an alias? So you can see how long it's been. ESPNV, that's what it is. And then I think we can do, yeah. Well, yeah, compost probe. Then we do the build. Hey, look at that. It didn't work. Static assertion failed. Why? I wish it would just give me the value. Non-template argument. Double is not yet supported. Non-type template argument. Double not yet supported. Are these two instances the same or different? Oy vey. Okay. File time print double. C++. Float? No. What is this? Compile time printer. I suspect it's a lot of work. Yikes. Okay. Huh. I guess I'll just have to print it at runtime. Like a loser. Let's do that. How are we printing stuff? Just using printf? Yeah. Alright. Oof. The problem is, I think... Did we do it with floating point off? No, I don't think we did. Okay. So maybe that will work. Printf. %f. Let's see. Using calibration value. %f. Calibration value. Okay. And we want to write that to calibration register. What page was that on? Below. Calibration register 5. What? Configuration register. Shunt. At PGA. Okay. Calibration register. Okay. Address 05. So, how do we do this? Dev.transmit. And we're gonna need some data here. So, an array. Uint8t. Well, I guess we're not ready for that yet. Powermon dot write calibration. That should print something out. I need to plug in the device. Okay. Oh, Build fail. Why? Failed. Hello world elf. That's a lot of text. Power monitor. Bush. What? Power monitor bus H. Eh? Oh. Yeah. Dev is bus. And adder. Yeah, constructor was not defined. All right. I think I'm just gonna do a few minutes of Geoguessr. Is it USB or ACM? Well, currently it looks like neither. Oh. Why isn't it coming up? Here it is. I don't see it. Oh, man. Yeah, this is that. That's not. It's not coming up. Why isn't it working? Okay. We have to figure this out now. USB 32, TTY, USB or ACM 0 not coming up. All right. created a new project based on the template. Compiles fine. Series ASP tool. Seems to select the wrong device file. Yeah, it's not showing up as... Oh, it's not showing up as... what it's supposed to. Tail varlog syslog. All right, D message. What? What? Pseudo tail. Man tail. Follow. What's big follow? Okay, so tail flag F. New. New. How to tail demessage. Looking for some combination of various things. Demessage flag W. Presumably for like watch. Give it some time. Okay, there. TTY star. Still not there. Ugh. Okay. Is it just like syncing too much? Okay, how about now? No? Try it again. One more try. So it shouldn't be there. I'm plugged in. Manufacturer expressive. And nothing changed. USB. What is it? USB devices? UDEV. No? What the heck? Also, what's all that flashing? That's concerning me slightly. GPIO? There's an LED toggle task. Maybe you should see what I'm trying to do here. It's not great. You couldn't see it, but that LED. I wish I could show you my mouse here and point at something. That guy. That flashes every once in a while randomly for no reason. To me, saying that it's like rebooting. I think. It's kind of what that says to me. Because that's GPIO 7, and it should be turning off every 5 seconds without without flashing like that. It should not be flashing. Yeah, so I don't know what's going on with that. Okay, that should be kind of an uncontroversial disconnect there. Let's try putting this back and seeing how it goes. Okay. Power it on. Okay. That's a lot of things for just being turned on. I don't see... Okay, how about now? No? This is annoying. Okay. Now. Okay. ESP32 dev kit force USB. Bootloader. Hang capacitor on enable signal. What's really extensive? Oh, I see. PDF. The back of an X-Acto blade. You mean the not sharp side? Solder 33 microfarad. Capacitor there. Okay. Okay. Now I'm holding this stupid thing. Let it discharge. Power on. Gosh. Okay. ESP32 S3 buttons into bootload. ESP tool. Do I have this? So I think it's press and hold boot, then press reset. Based on what it said here. GPI low when pressed. That's what I want. So now, it doesn't help me. Is there ESP tool? I've never used it. Right, the problem is it's not coming up at all. Let's see. What if we do ESP tool run and let it try to figure it out itself? I don't know that we're gonna have many success. Yeah. What the heck? Okay, here's something dumb. What if we flip it over? Nope. Hi. Troubleshooting. Oh boy. They say failed to connect. Processing serial port. Yeah, that's the problem. It's not showing up at all. Missing bootloader? No. Right, the problem is, yeah, it's not even showing up as a device. Bootloader won't respond. On Linux, read and write access to the serial port over USB is necessary. Dial out UDCP. Yeah, no, I have that. I'm pretty sure. Here, now you can do this using a serial terminal program. That's the thing, it doesn't show up at all. Okay. Alright, if board doesn't have a bridge, for boards with an installed USB to UART bridge, the connection between the personal computer and the bridge is USB, and the bridge ESP32 is UART. Yeah. I mean, sure. Connect it. Identify, blah, blah, list of things, FTDI. Specify baud. Check port. Note, macOS users. Yeah, That's really annoying. I had a third device I didn't want to necessarily use. Let me try a different cable. Okay, so there it is with a new cable. I don't see a difference. Ugh. Oh boy. How to debug USB rules. UDEV, that's what I mean. UDEV. Here we go. Okay. What's that? Sudo UDEV ADM control. Okay, and then okay. I've turned it on. That's a lot of debug stuff. Here we go. Device is queued, skipping, overridden file, J-Link rules, G-Photo? What the hell is G-Photo? Well, okay. For one, we know it's this device. ID with ID of that. That's what's important here. So can we find that in here? Sorry, talking in dinner with my wife. Okay. Rules. We're looking for whatever this device is. Oh, it's connected to a hub. So first is the hub. Sure. What did I say it was? VIA Labs, VL8 Hub. So those are like the same device. For some reason it shows up twice. Really? It's this. 303A. Where's our device? 303A. Default rules. Super speed USB device by VIA Labs. Sure. Oh boy. Why does it show up twice? That's interesting. Also a USB 2.0 hub. Interesting. USB 2.0 hub. That's it again. Okay, now we're talking. This device. Device is queued, forked off, blah 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 blah. Okay. Permissions, symbolic link there. It's not like the right. Wait. Yeah, 303A, that's the one. So then wait, where is it? Data C189 does not compute. There's this. MTP probe. Default rules. Yeah, it's not an MTP device. What the heck? What? Where is it? I'm so confused. Okay. Yoink that. Let's plug it in more directly. Get rid of the hub. Okay. So there it is. Still not there. Okay. Well, let me... I'll unplug it. Time goes by. Plugged in. There we go. Big dump. New device. This. Processing. UDEV rules default. No entry found. No data available. Built-in command. Starting off. Successfully forked. Yada yada. Here. That should be it, right? What the heck? Well, 303A 1001. That's there. Yeah, why? That should... Oh, whoops. That should just work. So I guess let me look at Etsy udev rules 99 expressive. Okay. So that's not working. I have the rules, and it's looking at them, but then it's like MTP failures. So ESP32 S3 MTP device. Okay, have you programmed it? Flash some code. You should see a port appear. What? What? How can you flash code to it if there's no port? Your own board design. My own board design. Okay. Alright, add some caps. Alright, sure. Pin config? No. Download mode, maybe? What is... chip boot control. Chip boot control of the technical reference manual. Boot mode control. Reset determine the boot mode after reset is released. Joint download boot mode supports the following methods: USB download, UART download, SPI download. Not gonna do it. Yeah, so I should be able to press the button and then press reset. And ideally, it should show up. Yet it does not. Ugh. What if... Okay. Unplug it. I'm gonna hold boot while it's getting plugged in. Is it now? No. Then I'm at a loss. Failed to run built-in. Like, what is this? Failed to run built-in hardware DB subsystem USB. Da-da-da. All right. ESP32 S3 UDEV rules. DFU util. Right. It's saying create that defuse rules. So etc udev rules 40. All right. Sudo edit. No. etc udev rules 40 dfus dot rules. Okay. What do we put in there? Well, let me make sure. Groups. I believe it's UUCP. Yeah. Or plug dev? Possibly both. Group. Say. We'll say plug dev. That's fine. Or maybe look at dev tty. UUCP is what they use. There. Okay. Close that. And then sudo udev adm reload. Okay. That's a bunch of rules. What is it complaining about? El Gato game capture, assuming equals. Yeah. Here's this one. We just added that. Did it work? Nope. Holy shnikes. Alright, hold down boot. Unplug. Replug. Say hello to... Yeah. I mean, I did the thing. Product. Group plug dev. You need to specify one of D or U. What is D? D. Download. foo.file. Yeah, I know it doesn't upload. foo.file. What is... Well, that's unrelated, though. OpenOCD, maybe? I mean, it's there, ostensibly. Disconnect processing device. udev failed to run. Udev rule failed to run built-in HWDB. Guess I don't know how UDEV rules work. Okay, so if I check T-message, I found the driver name in the last line here. I mean, it doesn't get any further than that. What is it supposed to look like when it works? Did that work? No. It also did not work. Ugh, I suspect a reboot is the only answer. That's annoying. I mean, I suppose I can, but it is 6:30, and I haven't even played Geoguessr. So maybe let's do that. Because I'm tired of this. All right. I'm not going to bother switching over to... Oh, we'll keep that around there. Maybe we'll just shove these over here. Yeah, I'm not going to bother updating the category, because last time that I tried doing this, .com. Last time I tried doing this, I had someone come in and just like immediately start spoiling and ruining the experience. Like, oh, you're here. And I'm like, well, where's the fun in that? I guess I'll do a daily challenge. I normally play on my phone, so I don't get to see a lot of this stuff. So we got Blue Ribbon Breads. Driving on the left side of the road. We got... Is it English? English language? There's a sign. Very hard to read. I can't tell. There's some more like signage over here. Wellness Center. Is that Afrikaans? I can't tell. So mountains in the distance, hillside. I'm gonna guess South Africa, maybe? We still got 2 minutes, though, so I'm not gonna go too fast here. Not sure what it's saying there. Thetsane Motors. I wonder if that's the name of this place. Minute left. That's fine. Ooh, taxi. They don't really say. MS? Yeah, this one also says Thetsane. I don't see where'd the sign go. Thetsane. There it is. Thetsane Hardware. I don't know what that is. I was thinking down here, but I could be wrong. Sneaky Lesotho, maybe? Possible. But usually, it's around here. Are there other English-speaking? I guess there are other places in Africa that also speak English. Was it Lesotho? Ah! It was Lesotho. What is that saying, though? That's saying west? Thetsane? Thetsane? Lower Thetsane? Yeah, I don't know. Maseru is the name? Alright. Not bad, not bad. Okay, this looks... like... Slavic? No? It's gone. They say stop. Looks like we're in the European Union based on the license plates. I saw there was a hydrant sign. Hydrant. No. What does the cab say? No, it's gone. All right, let's try to go slightly downhill. And see if we can't spot a kind of urban center of sorts. Oh. Grupul Anarom. Nuating Shalalala Suseava Delgaz Grid. Oh, I don't know. I don't know what I would guess. Is Lithuania in the EU? I don't know why I'm thinking Lithuania. Okay, so we went the wrong way. Found ourselves at a dead end. Shoot. Have we gone in a circle? Got a minute left. Oh. Sign. Devanza. Sef George. All right, I'm thinking maybe up in here or Croatia. Let's guess here. Although, I don't know, do they have hats on their A's in Croatia? I can't tell. I don't know. S with a Sadilla? Yeah, I think it's gonna be, you know, something around here, but I could be wrong. Could be up here. Ah, Romania. Oh well. Next. Is my stream dead? No? That's weird. Stream manager just unhappy. All right. Looks like we're in. Oh. That looks like there's some like size and lots of K's. So could be like Ukraine, Russia. I think that's Ukraine. If that's like an I. Oh yeah, I think I read that somewhere. I could be wrong. But where? Don't even know how to begin trying to say that. Near Kiev? I guess let's put it to the test, because I thought I read somewhere that if there's an I in it, then that means it's probably Ukraine. Whereas all these other places, they don't use I. Well, there's an I here. So, who knows? Could be Russia. Could be Belarus. Oh, is it I with dots? Oh, no. Okay. So maybe we'll do near Moscow. I don't know the other... I don't know the other tells. Yeah, I'm completely worthless when it comes to like Eastern Europe. When there's Cyrillic involved, it's game over. I gotta get quite lucky. Yeah. No, I should have gone with my gut. Was it Ukraine? Yeah, it was. Damn it. Oh well. Boo. Alright, where are we now? Oh. Got a little sign there. Backwards R. Street. Fariza Market. One interesting thing is that it's definitely not the US because there are no US flags. Let's see. Oh. Who's got threes? Bulgaria? Serbia? Not Moldova. Poop. Ooh. You got any info? No? Ugh. Yeah, I don't know. I'm so bad at these. I suppose it could be Russia. But I don't know. It looks kind of different than... Oh, I can't tell you. Maybe Russia. Somewhere down there. That's not a good guess. Kazakhstan. All right. All right, let's... Guys, I'm gonna wrap this up now. What the heck is this? Looks pretty cool. What's that? That's not like Christ the Redeemer. This is quite populated. Look at that. Can I super skip over there? Go, go, go. Go, go, go. There's a big wall. Come on, get me over there. All right. I'm thinking it's kind of Mediterranean. No. Aha. Shoot, is that Chile or... I think it's Chile. No? Oh, man. Or Costa Rica. Shoot, now I'm looking like a fool. Well, this is along the coast if it's in Chile, so what am I doing? So... like, there, maybe? Yeah, I thought Puerto Rico was like the triangles. The triangle star. Oh, now I'm doubting myself though. Oh no. What is that flag? Oh gosh. We've taken a turn. That's yellow and black checkers? That's an interesting one. Uh-oh. We've time skipped. Ah, all right. Nice. All right, that could have been way worse. Cool. All right, well, thank you for joining me. Didn't get much done. I did do a soldering, which is cool. And besides that, yeah, they just hung up on the actual device not really working properly, so that's freaking annoying. Yeah. I might log on tomorrow just because, to try to get more into the habit and like doing it more often. But otherwise, I will see you on Thursday. Catch you later.